This is Professor Corey from the Professor's DuBois channel. In our previous lecture on chemical equilibrium, we showed how to calculate an equilibrium constant for a chemical reaction using equilibrium concentrations of reactants and products. The value of the equilibrium constant allows us to determine if the reaction is product favored or reactant favored at equilibrium. We can sometimes calculate the equilibrium constant based on another reaction with a known value. This slide is just a summary of the manipulations that we covered previously. Remember that the equilibrium constant is calculated using product and reactant concentrations at equilibrium. In this problem, we're given concentrations, but they are not equilibrium concentrations. These are initial concentrations, so we need to determine what the equilibrium concentrations will be for all species given initial concentrations of the reactants and an equilibrium concentration for the product. Note that the product, hydrogen iodide, has a coefficient of 2, so the equilibrium concentration will have to be squared in order to calculate the equilibrium constant, or capital K. The method that we will use to determine equilibrium concentrations is called an ICE table. In this case, ICE is an acronym where I stands for initial, C stands for change, and E stands for equilibrium. You will set up a table similar to a data table for this technique. The initial concentration of the reactants was given in the problem, so we can enter these into our table in the initial row. If we had two reactants and mixed them together, initially we would have no product, so we can write 0 for our product, hydrogen iodide, in the initial row. We don't know how much the initial concentrations are going to change. All that we know is that the value will go down, and we know that we will form product, so this change will be an increase. We express the change in terms of x. Notice that the hydrogen iodide goes up 2x. This is because there are two hydrogen iodides in the balanced equation. Also notice that the equilibrium concentration for HI is also given, so we can write this in the equilibrium row. For our reactants, we can say that at equilibrium, we will have our initial concentration minus some amount that we will call x, or in this case, 1.00 minus x. If you look at the product, you will realize that there's enough information provided to solve for x. We can write 0 plus 2x equals 1.58 because we know the equilibrium concentration. Solving for x gives us 0.79. So our reactant concentration is 1.00 minus 0.79, or 0.21 molar. Here it is worked out for you. When you have a final concentration for either a reactant or product, you can determine the final concentrations for all species in a balanced equation using an ICE table. Once you have all of the equilibrium concentrations, you can solve for the equilibrium constant. For this problem, K equals 56.6. This is greater than 1, so we can say that at equilibrium, there will be more products than reactants, or we can say the equilibrium is product favored. Here's another one similar to the one we just completed. If you're feeling confident, you can pause the video and give it a try. In the next slide, I'll walk through the process. The first step is to set up an ICE table. I like to add the double arrow to help me separate reactants and products. For each reactant and product will have its own column. We are given the initial concentration for the reactant NOCl, and we know that initially there will be no products present, so we can enter 0 for the two products. The change is expressed in terms of x with careful attention to the balanced equation. The equilibrium concentration of the product NO was provided, so we can enter that in the equilibrium row. With the equilibrium concentration known, we can solve for x as shown in the lower left. Once we know x, we can determine the equilibrium concentrations for all species. Using the equilibrium concentrations, we can calculate the equilibrium constant. 0.080 is less than 1, so we can say that this reaction is reactant favored at equilibrium. This problem does not include any equilibrium concentrations, but we are given the equilibrium constant. To solve for the equilibrium concentrations, we will use an ICE table. Initial concentrations for the reactants are given, so we can enter them into the table, and again, it's safe to assume there's no product present initially. The change is expressed in terms of x, and again, we must use the balance equation for this. With no equilibrium constants given, we will simply write all of these in terms of x. We will write the equation for the equilibrium constant as before. K equals the equilibrium concentration of the product, hydrogen iodide, squared, divided by the equilibrium concentrations of the reactants. Putting the equilibrium values in results in this equation, notice that 1.00 minus x times 1.00 minus x is the same as 1.00 minus x squared. The numerator is also squared because the balanced equation has a coefficient of 2 for the product in this reaction. We can simplify this equation by taking the square root of both sides. On the left, we get 2x divided by 1.00 minus x. On the right, we take the square root of 56.6, which equals 7.523. At this point, we just have to solve for x. There are many ways to do this, but I would start by multiplying both sides by 1 minus x. This cancels on the left. On the right, we'll have to multiply by 7.523 using the distributive property. Now I will combine like terms, or add 7.523x to both sides. The last step is to divide both sides by 9.523, giving us our x value at 0.788. Once we have our x value, it is good practice to reread the question to remind us what we're looking for. This problem asks for the equilibrium concentrations of all species, so I have to go back to my ice table and put the value in for x at equilibrium to get the concentrations for all of the species. Some problems will require the use of a quadratic equation in order to solve for equilibrium concentrations, and this problem is an example. We start with our ice table and enter our initial concentrations. The change is represented in terms of x, and in the absence of any equilibrium concentrations, we will express our equilibrium concentrations in terms of x. We cannot take the square root for this problem because the denominator, N2O4, is not squared. Solving this problem results in an expression at the bottom of the image. Notice that 2x squared means that we square both the number 2 as well as the x. We cannot combine the x squared value with the x, so we'll need to use the quadratic equation to solve for x. We have to move all of the terms to one side of the equation, resulting in 0 on the other side. The number that precedes x squared is your a value, and the number that precedes x is your b value. The number with no x is your c value. You will get two answers when you solve the equation, but one of the values will not make sense. My advice is to complete the calculation in small steps to reduce the chances of error. One of our values is negative, and this does not make sense. This would suggest that our product went from 0 to a negative number, and this is not possible. So the 0.027 must be the correct result. The next step is to find the equilibrium concentrations, which is relatively simple once we know the value of x. While this looks intimidating, the quadratic equation can be cumbersome, but it's not extremely difficult to solve. Recall that each of the scenarios involved using an ice table. In our next lecture, we will practice more with ice tables and introduce a method of avoiding the quadratic equation, and we'll also explore methods of determining if a chemical reaction is at equilibrium. Stay tuned for more chemistry with the Professor's DuBois.